Have you ever paused to think about the incredible journey your data takes just to get across, say, your living room, let alone the entire world?
Yeah, you hit send on an email or tap to load a web page, and poof, it seems like it's just there.
Exactly. But what invisible, really critical steps make that happen? Today, we're pulling back the curtain on one of the most fundamental, yet often unseen, parts of that digital expedition.
We're embarking on a deep dive into the link layer in LANs, drawing from a classic text, computer networking, a top-down approach.
Ah, Kurose and Ross. Excellent source.
Definitely. And this layer is really where the digital information you create meets the physical reality of cables and wireless signals.
Right, it's that crucial stage that moves your data from one device to its immediate neighbor, the very first step.
Precisely. Our mission today is to demystify exactly how your network layer information, like an IP datagram, gets securely packaged up.
And sent across that very first leg of its journey, we'll explore the fundamental rules of the road that let devices share a communication link.
And also how local networks are built and managed, from the simplest home connection all the way up to the massive scale of a data center.
Okay, so to help visualize this, you often use an analogy, right?
Yeah, let's think of your data as a tourist on a complex, multi-layered journey. If the entire trip from maybe Princeton, New Jersey, all the way to Lausanne, Switzerland, if that represents your complete datagram,
Okay, the whole message.
then each individual segment of that journey, like a limousine ride to the airport, then the plane flight, then a train trip, each segment is like a link.
Got it. And the companies managing those segments, the limo service, the airline.
They're essentially the link layer protocols.
Yeah.
Their job is making sure our tourists get safely and reliably from one adjacent stop to the very next one.
Even if each leg uses totally different modes of transport, a limo is not a plane.
Exactly. That's the core idea of the link layer. It's all about that immediate hop between adjacent devices, managing the specific transport for that hop only.
So fundamentally, the link layer takes that datagram, our tourist, and moves it from one node to an adjacent node.
Right. And a node could be your computer, a router, switch, even a Wi-Fi access point, anything connected along the path.
Okay, when we talk about these links, are they all the same? Or are there different types?
Good question. No, they're not all the same.
Mm.
Links basically come in two main flavors.
Okay.
First, you've got broadcast channels. Think of wireless LANs or maybe older satellite networks. Lots of devices share one single communication channel, like everyone tuning into the same radio station.
Makes sense. Everyone hears everything. And the other type.
That's point-to-point links.
Mm-hmm.
These are direct, dedicated connections just between two devices, like a router talking directly to another router, or maybe your computer plugs straight into an Ethernet switch with a cable.
One-to-one. Much simpler, I imagine.
Generally, yes. And to make sure our data tourist travels accessibly across these different links, the link layer provides some essential services.
Okay, what's job number one?
Well, it needs to package the data correctly for that specific journey segment. This is called framing.
Framing, like putting it in a box.
Sort of. Think of it like a specialized shipping container designed specifically for that particular road or airline. The link layer wraps the network layer datagram inside a link layer frame.
And this frame has extra info.
Yes, it adds crucial details in header and maybe trailer fields info that's only relevant for that one hop. This is how different physical technologies like Ethernet versus Wi-Fi can both carry the same underlying IP packet. They just use different containers, different frames.
Okay, that makes sense. Now, what about when lots of devices are trying to use the same link, like on Wi-Fi? How do you avoid a massive traffic jam?
Ah, that's the job of link access, or more formally, medium access control, MAC.
MAC. Heard that acronym before.
Right. For those busy broadcast links, imagine a bustling intersection. Every car wants to go at once. MAC protocols are like the digital traffic rules.
So traffic lights, stop signs, that
Yeah.
kind of thing.
Exactly. Coordinating who gets to transmit data and when, preventing total chaos and collisions. Now, for point-to-point links, it's much simpler.
Because there's only one car on the road at a time.
Pretty much, so no complex traffic control is needed there.
Okay, framing, link access. What about making sure the data actually arrives correctly? Reliable delivery seems crucial.
It does, doesn't it? But reliable delivery at the link layer is actually listed as optional.
Optional. Why would you not want reliable delivery? That feels weird.
It's a really good question, and it gets to a core design principle in networking: efficiency and avoiding redundant work.
How so?
Well, for noisy links, like wireless connections where interference can easily cause errors, reliable delivery is crucial. The link layer uses acknowledgments and retransmissions, much like TCP does at a higher layer.
Okay.
But it fixes errors locally, right on that specific link. This stops a small local error from causing a big end-to-end retransmission delay involving the original sender.
Ah, fix it quickly where it happened. Makes
And
sense, so why optional?
because for clean wired links, like fiber optic cable or even high-quality copper, the error rate is incredibly low, almost negligible.
So adding all that acknowledgement and retransmission stuff.
Is mostly unnecessary overhead. It
Mm.
just slows things down. If the link is virtually perfect, you skip the reliability checks at this layer for raw speed, knowing higher layers like TCP can handle the very rare error that might slip through.
Interesting trade-off. Speed versus guaranteed local delivery based on the link's quality. Okay, beyond retransmissions, how else does the link layer handle potential data corruption? Bits flipping and all that.
Right, the physical world is messy. Bits can flip, a 0 becomes a 1, or vice versa due to electrical noise, interference, cosmic rays, whatever.
So we need error detection and correction.
Exactly. The link layer tucks special error detection bits into the frame.
Yeah.
These let the receiver check if the data got garbled during transit.
Detect the error. Can it fix it too?
Sometimes. Some more advanced techniques can actually correct certain errors without needing a retransmission. Pretty clever stuff.
Okay, how does that work? Let's start with detection.
The simplest concept is parity checks. Imagine you're sending a string of bits, say 7 bits. You add an 8th bit, the parity bit.
And this bit depends on the others.
Yes. In even parity, you choose the parity bit, 0 or 1, so the total number of 1s in the 8 bits is even. The receiver counts the 1s. If it gets an odd number, it knows an error occurred.
Simple, but hang on. What if 2 bits flip? Or 4? Any even number?
Ah, you saw the limitation. An even number of bit flips would result in an even count of 1s again. The parity check wouldn't catch it.
So single parity is pretty weak against burst errors where noise might corrupt several bits close together.
Exactly. It's too simple for most real-world links. That leads to smarter methods, like two-dimensional parity.
Two-dimensional, how does that work?
It's quite neat. Imagine arranging your data bits in a grid, like rows and columns in a spreadsheet.
Okay.
You calculate a parity bit for each row, just like before, but you also calculate a parity bit for each column.
Ah, parity bits down the side and across the bottom.
Precisely. Now, if a single bit flips somewhere in that grid,
Its row parity will be wrong, and its column parity will be wrong.
exactly, the receiver can use the intersection of the bad row and bad column to pinpoint the exact flipped bit.
And if you know which bit flipped,
You can just flip it back, correct the error on the spot. This is a form of forward error correction, or FEC.
wow, that's powerful, especially useful where retransmissions are slow or impossible like.
Deep space communications.
Yeah.
Or real-time streaming where delays are bad.
Okay, so parity is one way. I've also heard of checksums.
Yes, checksumming methods are common, often used at higher layers like TCP and UDP in the internet stack.
How do they work generally?
They basically treat the data as a sequence of numbers, sum them up in a specific way, and send that sum, or a variation of it, along with the data. The receiver does the same calculation and compares the result.
Simpler to do in software, maybe?
Generally, yes, but they offer relatively weaker protection compared to what the link layer often needs, especially for detecting certain kinds of common errors on physical media.
So for the link layer, especially in hardware, we need the real workhorse.
We do. And that's typically the cyclic redundancy check, or CRC.
CRC. Okay, sounds serious.
It is. It's the standard for robust error detection in technologies like Ethernet, Wi-Fi, disk drives, lots of places. It's implemented directly in hardware on your network adapter for speed.
How does it work without getting too mathematical?
Okay, the gist is this. It treats the data bits as representing coefficients of a long polynomial. Both sender and receiver agree beforehand on another fixed polynomial called the generator.
Like a secret key?
Sort of. The sender performs a special kind of polynomial division, using modulo 2 arithmetic, which is just XOR operations really fast in hardware, of the data polynomial by the generator polynomial. The remainder of this division is the CRC value.
Okay, a remainder.
The sender appends this remainder, the CRC bits, to the original data. The receiver gets the data plus the CRC bits and performs the same division using the same generator.
And if everything arrived perfectly?
The remainder should be 0. If it's anything other than 0, an error has been detected.
And this catches errors better than parity or simple checksums.
Immensely better. CRCs are specifically designed to catch common types of errors, like burst errors spanning multiple bits with extremely high probability. It's very, very robust.
Okay, powerful error detection with CRC. We've got framing, link access, error handling. That covers getting data cleanly between two neighbors. But what about that cocktail party problem you mentioned? The broadcast links where everyone wants to talk.
Right, back to the shared channel. That's where multiple access protocols come into play. We need rules for who talks, when to avoid collisions, everyone talking over each other.
Like at a real party, if everyone shouts at once, nobody hears anything. So what makes an ideal protocol for this digital party?
Well, ideally you'd want a few things. One, if only one person wants to talk, they should get the full speed of the channel, no waiting.
Makes sense. Don't waste capacity.
Two, if many want to talk, they should share the channel fairly. Three, it should ideally be decentralized. No single-party host controlling everything, because that host could fail.
And simple, right? Easy to implement.
Always a goal. Now, we can group these protocols into roughly three main categories.
Okay, what's the first type?
Channel partitioning protocols. These basically slice up the channel resource time, frequency, or code, and give each node its own dedicated piece.
Like assigning seats at a table?
Kind of.
Yeah.
Time division multiplexing, TDM, gives everyone a fixed, repeating time slot. Your turn comes, you talk. If it's not your turn, you wait.
Pros and cons.
Pro, no collisions, perfectly fair allocation. Con, wasteful if you have nothing to say during your slot, or if you have urgent data but have to wait for your turn even if the channel is idle.
And frequency division multiplexing, FDM.
Similar idea, but divides the channel into different frequency bands, like giving each device its own private radio station. Same pros and cons as TDM, basically.
Oh, you mentioned code.
Right, code division multiple access, CDMA, is more sophisticated. It assigns a unique code to each user. Users can transmit simultaneously in the same frequency band, but because of the codes, the receivers can pick out the signal intended for them.
Ah, clever math separates the signals. Used in cell phones, you said.
Yep, particularly common in 3G networks. Allows many users to share the same frequency spectrum efficiently.
Okay, so partitioning is one way. What's the next category?
Random access protocols. These are more, let's say, optimistic or chaotic. Nodes don't get a reserve slot. They just try to send when they have data.
And hope for the best. What if two try at once?
Then you get a collision. And the protocols define how to detect that collision and recover, usually by waiting a random amount of time before trying again.
The original here was ALOHA, right? Developed in Hawaii.
That's the one. In its simplest form, tier ALOHA, a node just transmits immediately. If it collides, wait random time, try again. Very simple, fully decentralized.
But probably not very efficient. Lots of collisions.
Exactly. Maximum efficiency is quite low, maybe 18% of the channel capacity. A slight improvement was slotted ALOHA.
How did that work?
It synchronized transmissions into fixed time slots. You can only start transmitting at the beginning of the slot. This reduces the window for collisions to occur.
Better, but still limited.
Better, yes. Efficiency goes up to about 37%. Still means a lot of wasted potential due to collisions or empty slots. This led network designers to think, can we be smarter?
Which brings us to CSMA, carrier sense multiple access.
Right. The key idea. Listen before speaking. Before transmitting, a node checks if the channel is currently busy, if it senses a carrier signal. If it's busy, wait. If it's idle, transmit.
That sounds much better. Should eliminate most collisions, shouldn't it?
You'd think so.
Okay, so
But here's the catch. There's propagation delay.
the time it takes the signal to travel.
Exactly. Imagine two nodes at opposite ends of a long cable. Node A listens, channel is idle, starts sending, but its signal takes time to reach node B.
So node B might listen before A's signal gets there.
Think the channel is idle and start sending too. Boom, collision. Even though both listened first.
Ah, like that awkward moment in video calls where people talk over each other briefly.
Precisely. It's the digital version of that. So listening first isn't foolproof.
So how do we fix that?
We add collision detection, CD. This gives us CSMA-D. The rule becomes listen before speaking, but also listen while speaking.
Okay, so if you start talking and hear someone else.
You immediately stop, you detect the collision, transmit a brief jam signal to ensure everyone knows a collision occurred, and then wait a random amount of time before trying the listen then send process again.
And the waiting time is clever too, right? Binary exponential back off.
Yes. With each successive collision for the same packet, the node doubles the range from which it picks its random waiting time. This helps to quickly spread out nodes that are repeatedly colliding.
Very adaptive. And this CSMCD is the basis for.
Classic Ethernet. The original shared media Ethernet networks relied heavily on CSMA-D.
Okay, so partitioning, random access. What's the third category?
Taking turns protocols. These try to get the best of both worlds. Less randomness than ALOHA or CSMA, but more flexibility than rigid TDM or FDM.
How do they manage turns?
One way is the polling protocol. You have a master node that polls each of the slave nodes one by one. Do you have anything to send?
So the master controls everything.
Right. It eliminates collisions completely because only the polled node transmits. But you have polling delay waiting for your turn. And if the master fails, the whole network might stop. Bluetooth actually uses a form of polling.
Interesting. Another way.
Token passing. Here, a special short message, the token, is passed from node to node in a predefined order, often around a logical ring,
And only the node holding the token.
is allowed to transmit data. When it's done, or after a time limit, it passes the token to the next node.
Efficient, no collisions, decentralized.
Ugh.
Sounds good. Downsides.
Complexity. What if the token gets lost? What if a node holding the token crashes? Recovering from those situations can be tricky. Token ring and FDDI were examples of this.
It's fascinating how many different strategies there are just to share a single wire or frequency.
And real-world systems often mix and match. Look at Duo CSIS, the standard for cable internet.
How does that work?
It's a hybrid. It uses FDM to divide the cable spectrum into channels. The upstream channel, modem to head end, uses TDM-like mini-slots, but modems have to request those slots using a random access method, CSMA-like with backoff, in special contention periods. It's quite sophisticated.
Wow. Okay, so we've got the rules for sharing the road. Now, how do devices on a local network, maybe connected by switches, actually find each other? We need addresses, right?
Absolutely. This brings us to addressing and switching. We know about IP addresses for global identification.
Yeah.
But at the link layer, your network adapter, the actual hardware card, has its own address.
The MAC address, Media Access Control Address.
Exactly. Think of it like this. Your IP address is like your postal address. It's logical, hierarchical, and it changes if you move your computer to a different network.
Okay. And the MSC address?
That's more like the serial number stamped onto the device itself.
Mm-hmm.
Or maybe like a social security number. It's supposed to be globally unique, flat, not hierarchical, and permanently assigned to that network adapter by the manufacturer, following rules set by the IEE.
So every network card in the world has a unique MAC address.
Wow. Why two addresses, though? IP and MA.
It's key to the layering principle. It keeps the network layer, IP, independent from the link layer, MA. It also means that when a frame is sent on your local network, like your home Wi-Fi, not every single device needs to process it all the way up to the IP layer.
How does that work?
Your network adapter physically filters incoming frames. It only accepts and passes up frames addressed to its own MMAS address or to a special MA broadcast address, which is FFFFFFFFFFF in hexadecimal.
The broadcast address means everyone on this local network, listen up.
Precisely. All other frames addressed to other MS on the same network segment are just ignored by your hardware. Saves a lot of processing. Okay, but here's the puzzle. My application wants to send data to an IP address. The link layer needs a NAC address to actually send the frame on the local network. How does it get the MSC data corresponding to that local IP address?
The missing link. That's the job of the unsung hero. ARP, the Address Resolution Protocol.
ARP. Okay, what does it do?
ARP translates an IP address into a MAC address, but only for devices on the same local subnet.
How? Does it keep a big list somewhere?
Sort of. Each device maintains an ARP table in its memory. A cache mapping recently used IP addresses to their corresponding MA addresses on the local network.
So if the IP is already in the table.
Great. Your device just looks up the MSC address and builds the Ethernet frame. But if the IP address isn't in the table,
Then what? Shout for help.
basically, yes. Your device constructs an ARP query message. This message essentially says, who has IP address XYZW? Please tell me sender IP your MAC address.
And how does it send this query if it doesn't know the destination MA?
It puts the ARP query into an Ethernet frame, but it uses the broadcast MSC address, FFFFFFFFFFF, as the destination.
So every device on the local network receives and processes this ARP query.
Exactly. Each device checks if the requested IP address in the query is its own. If it is, that device sends an ARP reply message directly back to the original asker, using the asker's MSC address, which was in the ARP query.
And that reply contains the ART address the asker needed.
Correct. The asker receives the reply, extracts the MSC address, uses it to send its original data packet, and importantly, updates its ARP table with the new IP to MAC mapping so it doesn't have to ask again right away.
That's really clever. And it's automatic, right? Plug and play.
Totally. ARP builds its table dynamically, makes setting up local networks much, much easier.
Okay, one more ARP scenario. What if the destination IP address is not on my local network? Say it's Google's server across the internet. Does ARP still work?
ARP is still involved, but indirectly. Your computer knows the destination IP is not local, so it needs to send the packet to its default gateway router.
The device that connects my local network to the outside world.
Right. Your computer might not know the router's MAC address initially, so it will use ARP to find the router's MC address based on the router's known IP address, which your computer usually learns via DHCP.
So the Ethernet frame containing the packet for Google is actually addressed at the link layer to the router's MC address.
Exactly. The router receives the frame, unwraps the IP datagram inside, sees the final destination IP, Google, consults its routing table, and then forwards the IP datagram out on the next appropriate link, creating a new link layer frame for that next hop.
Fascinating. ARP is the local translator, getting the packet just to the edge of the local network if needed.
Precisely. Now let's talk about the dominant technology for wired LANs, Ethernet.
King of the hill for decades now. Why has it been so successful?
Several reasons. It was one of the first high-speed LAN technologies. It's relatively simple and cheap to implement. And critically, it has constantly evolved its speed from 10 megabits per second originally up to hundreds of gigabits per second today, while maintaining some backward compatibility.
How did it start?
The original Ethernet used coaxial cable in a bus topology. All devices shared the same cable, making it a true broadcast medium. It used that CSMA protocol we discussed earlier.
Listening, sending, detecting collisions.
Then came hub-based star topologies. Devices connected to a central hub. Looked like a star, but the hub was just an electrical repeater. It was still a single shared broadcast domain, still using CSMA, still prone to collisions.
So just a neater way to wire the same old bus. But modern Ethernet is different, right? It uses switches.
That's the huge leap. Today, Ethernet almost universally uses a switch-based star topology. You connect your devices to an Ethernet switch.
And these switches are smarter than hubs.
Much smarter. They are true store and forward packet switches, operating at layer 2, the link layer. They read the destination MAC address in incoming frames and intelligently forward the frame only out the specific port connected to that destination or the port leading towards it.
So no more broadcasting every frame to everyone.
Not usually, no. This has two massive benefits. First, it dramatically reduces unnecessary traffic on links. Second, because each port on a switch is essentially its own isolated collision domain.
Collisions are basically eliminated, and devices can operate in full duplex mode.
Exactly. Sending and receiving data simultaneously on their connection to the switch, without worrying about collisions. This means for modern switched Ethernet, CSMA is often turned off or simply not needed anymore.
Wow, so the protocol that defined early Ethernet is now largely obsolete on modern networks. That's evolution.
It really is. But what's amazing is, despite the huge changes in speed and topology, bus to star, hub to switch, the fundamental Ethernet frame format itself has remained remarkably consistent.
The structure of that shipping container has stayed the same. Impressive design.
Absolutely. Now, how do these switches work their magic? Their core job involves filtering and forwarding.
Based on MAC addresses.
Yes. Each switch maintains a switch table, sometimes called a MAC table or CAM table. This table maps destination MS addresses to the switch interface port leading to that MAC address, and usually includes a timestamp.
How does the table get built? Do you have to configure it?
Nope. This is the really elegant part. It's self-learning. The switch builds its table automatically by examining the source MAC address of every frame that arrives at each port.
So when a frame comes in from device A on port 1, the switch learns device A's MC is reachable via port 1 and adds it to the table.
Precisely. And these entries have an aging time. If the switch doesn't see any traffic from a particular MAC address for a while, say 5 minutes, it removes that entry from the table, keeping it up to date.
Plug and play again. Makes deploying switches super easy.
Definitely. So when a frame arrives at a switch port, the switch looks up the destination MAC address in its table. 3 possibilities.
Okay, case 1.
The destination MAC address is not in the table. The switch hasn't learned where it is yet. In this case, the switch acts like an old hub it floods, or broadcasts the frame out all ports except the one it arrived on.
Hoping the destination device is out there somewhere and will maybe reply, allowing the switch to learn its location.
Exactly. Case 2. The destination MAC is in the table, and the table says it's reachable via the same port the frame arrived on.
Meaning the sender and receiver are on the same connected segment already?
Right. In this case, the switch performs, filtering it just discards the frame because there's no need to forward it anywhere else.
Prevents unnecessary traffic loops. And case 3.
The destination MAC is in the table, and it's associated with a different port than the arrival port. This is the normal case. The switch performs forwarding. It sends the frame out only on that specific port indicated in the table.
Efficiently directing traffic only where it needs to go. That's the core intelligence of a switch.
That's it. Now, this often leads to the question, what's the difference between switches and routers? They both connect network segments, right?
Yeah, they sound similar in function sometimes.
But they operate at different layers and have different strengths and weaknesses. Switches, as we said, are layer 2 devices. They use MAC addresses.
Plug and play, very fast, filtering forwarding within a local network, eliminate collisions.
Right. But they have limitations. They don't stop layer 2 broadcast storms. If one device goes haywire and floods the network with broadcast frames, like ARP requests or DHCP discovers, the switches will dutifully forward those broadcasts everywhere within the switch network, the broadcast domain.
That could grind the network to a halt.
It could. Also, to prevent endless loops where frames circle between switches forever, switch networks must run protocols like Spanning Tree Protocol, STP, which logically disable redundant paths, limiting optimal routing and potentially slowing recovery from failures.
Okay, so switches are great locally, but have some scaling and robustness issues. What about routers?
Routers operate at layer 3, using IP addresses. They are not plug and play. They need IP configuration for each interface. Historically, processing IP headers and running routing algorithms made them slower per packet than switches, though modern routers are incredibly fast.
But they have advantages.
Huge advantages for larger networks. Because they work with hierarchical IP addresses, they can manage much larger, more complex topologies. They inherently break up layer 2 broadcast domains. A broadcast frame arriving at a router interface stops there. It's not forwarded.
Acting like a firewall for broadcast storms.
Exactly. Routers can also intelligently choose the best path among multiple redundant links using sophisticated routing protocols like OSPF or BGP, handle network congestion, and implement security policies.
So the bottom line, switches versus routers.
Switches are ideal for building fast, efficient local network segments, LANs. Routers are essential for interconnecting different networks, like connecting your home LAN to the Internet ISP's network, or connecting different corporate departments, providing scalability, broadcast control, and intelligent path selection. Most real networks use both. Switches to connect end devices within a subnet, and routers to connect subnets together into the wider world.
That makes sense. Using the right tool for the job. Now, as networks get bigger, even within one organization, managing all those switches and keeping things organized must get challenging.
It definitely does. Imagine a large university campus or corporate building with hundreds or thousands of users spread across floors, needing different levels of access, maybe moving offices. Managing that with just physical switches becomes messy.
How do network admins handle that complexity?
One key technology is VLANs, virtual local area networks.
Virtual LANs, so not physical.
Right. VLANs allow a network administrator to take a single physical switch and logically divide its ports into multiple isolated broadcast domains. It's like carving up one big switch into several smaller independent virtual switches.
So ports 1 to 8 could be VLAN 10, say sales. Ports 916 could be VLAN 20 engineering, even though they're on the same physical box.
Exactly. And traffic within VLAN 10 stays within VLAN 10. Devices in sales can talk to each other, but their broadcast traffic, like ARP requests, won't reach the engineering VLAN, and vice versa, even if they are plugged into the same physical switch.
That provides traffic isolation and better security. What if sales needs to talk to engineering?
For traffic to go between VLANs, it must pass through a layer 3 device, a router, or a layer 3 switch. This allows for policy enforcement and control communication between the logical groups.
Very flexible. How does this work if you have multiple physical switches across a building and need VLAN 10 on all of them?
You use VLAN trunking. A special link called a trunk link is configured between the switches. This trunk link can carry traffic for multiple VLANs simultaneously.
How does the receiving switch know which frame belongs to which VLAN?
When a frame goes onto a trunk link, the switch adds a special VLAN tag defined by the IE 802.1Q standard into the Ethernet header. This tag contains the VLAN IT, like 10 or 20. The receiving switch reads the tag, knows which VLAN the frame belongs to, removes the tag, and forwards the frame only to ports belonging to that specific VLAN.
So VLANs let you group users logically, regardless of physical location, and control intergroup communication. Powerful stuff for large networks.
Absolutely. And this idea of virtualization extends further. We can think of an entire complex network acting like a single link from the perspective of the layers above it.
Like how dial-up internet used the whole phone network but looked like one link to your computer.
Exactly. A modern example is MPLS multi-protocol label switching.
MPLS. Often see that associated with ISPs and large enterprise networks. What is it?
MPLS allows network operators, like ISPs, to treat their large, complex backbone network almost like a giant Layer 2 switch, but with more intelligence. It speeds up packet forwarding compared to traditional IP routing.
How does it speed things up?
Instead of routers doing a full, complex IP address lookup at every hop, MPLS assigns a short fixed-length label to packets as they enter the MPLS network. Routers inside the MPLS core, called label switch routers or LSRs, then make forwarding decisions based only on this simple label, using it to index into a table that tells them where to send the packet next and what the new label should be. It's like putting a temporary simplified address sticker on the packet for its journey through the MPLS cloud.
Faster lookups. What else can MPLS do?
Its real power lies in traffic engineering. Because paths, called label-switched paths, or LSPs, can be pre-established based on labels, operators can explicitly route specific types of traffic along particular paths through their network, perhaps for performance reasons or to meet service-level agreements, even if normal IP routing would choose a different path.
So more control over how traffic flows.
Yes, much more granular control. It's also used for fast rerouting around failures, and is a common technology for building virtual private networks, VPNs, for corporate customers, creating logically isolated networks over the shared ISP infrastructure.
MPLS sounds powerful but complex. With software-defined networking, SDN, offering centralized control, is MPLS still the future?
That's a big debate. SDN offers a different way to achieve similar goals, often with more flexibility. MPLS is deeply embedded and performs well. They might coexist for a long time, or SDN might gradually take over certain functions. It's an evolving space.
Okay, let's shift gears to the ultimate in large-scale networking. Data center networking, the engines behind the cloud.
Right, think Google, Amazon, Microsoft Azure. These are warehouses filled with potentially hundreds of thousands of servers, all needing to talk to each other and the outside world with incredibly high speed and reliability.
What does the typical architecture look like inside?
It's usually highly structured and hierarchical. Servers' blades are mounted in racks. At the top of each rack, there's a top-of-rack TOR switch.
Connecting all the servers in that rack.
Exactly. Then, multiple TOR switches connect upwards to an aggregation layer, maybe Tier 2 switches, and those connect up to a core layer, Tier 1 switches. Finally, these core switches connect to border routers that link the data center to the public internet.
A multi-layered pyramid of switches.
Pretty much. And somewhere in there, usually near the edge, you'll find load balancers. Their job is crucial. Distribute incoming client requests, like web traffic, across potentially thousands of identical back-end servers.
Spreading the work evenly and handling server failures. Do they do anything else?
Yes, they often perform functions like SSL termination and can act like a NAT gateway, hiding the internal IP addresses of the servers from the outside world, which adds a layer of security.
Now, all those tiers, does communication between servers in different racks ever become a bottleneck? Like if a server in rack 1 needs to talk constantly to a server in rack 50?
That's a major challenge. In a simple tree hierarchy, all that traffic has to go up from 2R1 to maybe a Tier 2 switch, then potentially up to Tier 1, then back down to Tier 2, and finally down to TR50. Those higher-level links and switches can definitely become congested.
So how do data centers overcome this?
Several strategies. One is simply building networks with much richer interconnectivity between the tiers, moving away from simple trees towards architectures like close networks, or fat trees, which provide many parallel paths between any 2 points.
More roads available.
Exactly. And they use multipath routing protocols like ECMP, equal cost multipath, that actively spread traffic across all available paths between 2 points, improving both bandwidth and resilience.
Makes sense. What are the big trends driving data center networking now?
Massive focus on cost reduction, extreme automation, using SDN principles for managing thousands of devices, deep virtualization where VMs can move freely, and designing for unique physical constraints like ultra-low latency requirements, and managing tiny buffers and high-speed switches effectively, which often requires custom hardware and specialized congestion control algorithms. Modularity, like shipping container data centers, is also big.
Incredible scale and complexity. Okay, we've covered a ton of ground, from basic links to massive data centers. To wrap it all up, let's trace that everyday example. Bob connecting his laptop to Wi-Fi at home and fetching www.google.com. How does the link layer play its part throughout?
Perfect way to synthesize. So Bob turns on his laptop. First thing it needs is network configuration.
An IP address, gateway DNS server.
Right, it uses DHCP. Bob's laptop crafts a DHCP discover message. This message is UDP inside IP, but needs to go out on the local network. So it's encapsulated in an Ethernet frame.
Destination MIC address.
Broadcast. FFF, FFFF, FF, FF, FFF, FFF. The Wi-Fi access point sends this out over the airwaves, using Wi-Fi's own MSC protocols, like CSMA. Any device listening, including the home router, which usually acts as the DHCP server, receives it.
The router hears the plea for an address,
Allocates an IP address, gateway IP, etc., and sends back a DHCP offer or ACK message. This is also UDP inside IP, but now it's sent back in an Ethernet frame addressed directly to Bob's laptop's specific MSC address.
because the router learned Bob's MEA from the incoming discover request. The access point forwards this unicast frame just to Bob. Okay, Bob has an IP. Now he types www.google.com.
Router needs Google's IP address, time for DNS. Bob's laptop creates a DNS query, UDP, inside IP, destination DS server IP. But to send this packet off the local network,
It needs the MSC address of the default gateway router.
right, so first an ARP request goes out. Who has the router's IP address? This goes in an Ethernet broadcast frame.
Router replies with an ARP reply. That's me. Here's my ITME address. Sent in an Ethernet unicast frame back to Bob.
Bob's laptop now knows the router's ME. Now it can send the DNS query packet. It puts the IP datagram, destined for the DNS server, inside an Ethernet frame addressed to the router's MC address.
The router gets the frame, sees it's ME, processes it, looks at the IP datagram inside, sees the destination is the DNS server out on the internet.
Consults its routing table, and forwards the IP datagram out its WAN interface towards the ISP, creating a new link layer frame appropriate for that next link. Could be Ethernet, PPP over DSL, DCSIS, etc. The packet travels across the internet, hop by hop, router by router, each hop involving link layer framing and forwarding.
Until it reaches the DNS server. The server looks up Google's IP and sends a reply back. Same process in reverse, different link layer frames at each hop, until the reply, in an Ethernet frame from the router, reaches Bob's laptop.
Okay, Bob's laptop now has Google's IP address. Finally, time to fetch the page. Browser initiates a TCP connection to Google's IP, sends a TCP SYN segment.
Which goes inside an IP datagram, which goes inside an Ethernet frame addressed to the router's MSC address.
Which the router forwards out, travels across the internet, reaches Google's server. Google responds with SYN ACK. It comes back. Bob sends ACK. The TCP three-way handshake is complete, all thanks to countless link layer operations at each hop.
And then the actual HTTP GET request for the web page follows the same path, encapsulated hop by hop, and the HTML content comes back the same way.
Exactly, frame by frame, link by link.
Wow. When you break it down like that, it's just an incredible, almost invisible ballet of protocols working together perfectly. Framing, addressing, error checking, sharing the channel, all happening constantly for every single thing we do online.
It really is. We've peeled back the layers today to see how data travels those invisible highways. From ensuring error-free transmission with CRC, to coordinating shared channels with MAC protocols, to intelligently forwarding traffic with switches using ARP and MA addresses, the link layer is truly foundational.
So what's the final thought for you, our listener? Every single time you click, stream, or connect, you are relying on this incredibly intricate dance of bits and protocols, much of it happening right there at the link layer.
And with everything moving towards 5G, the Internet of Things, the ever-expanding cloud, understanding these fundamentals isn't just for network engineers anymore. It's really about appreciating the hidden complexity, the layered genius that underpins our completely interconnected world.
What might seem like magic is actually just really clever engineering and collaboration, built up layer by layer, from the smallest local link connecting your device to the router, all the way up to the vast global network.
Next time you connect, maybe just take a moment to ponder that unseen journey your data just took, starting with that very first hop managed by the link layer.